Hi, I'm Mariam, and I'll be introducing our second lab in Physics 2211, the motion of a falling object. Here we have the index of what will be included in this presentation. Let's start with the introduction. The purpose of this lab is to track and analyze the motion and position of a scrunched up paper that is dropped from a specific height using a software called Tracker. Our aim is to have the experimental model created using Tracker as accurate and precise to the theoretical model created using GlowScript. The main result of this lab is that the computational model, where the drag is considered, has more similar results to the experimental model than the computational model that considers the drag negligible. Moving on, let's introduce the physics principles. We have two main laws. Newton's first law that states an object in motion or at rest will stay in motion or at rest unless acted upon by an external force. We know that the scrunched up paper will continue to fall until the floor applies a normal force on it, causing it to stop. For our second law, it's Newton's second law, which is more commonly known as F is equal to ma, but here it is rewritten for us to find the velocity. Here is the experiment. We used a paper, a meter ruler, a video camera, a balance. And for our systems or surroundings, we took the video in a stable weather where there's no wind, so that there's little displacement in the x direction. The other forces acting on the paper were the gravitational force due to Earth and the drag that was acting upwards. Here is my GlowScript code. We changed the ball position to our initial position that is found through Tracker. And through trial and error, we found the constant b. Obviously, when we considered the drag negligible, our b was 0. We changed the condition of the loop to t is less than 0.13 because that's the time of the paper falling. And for the F net, we added the weight and the drag together. Here, the weight is a negative because we're taking the downwards direction as negative. If you look at the equation on the left, we can see that it is written in the format of y is equal to c plus mx, where the gradient is the acceleration, and we know that our acceleration will be changing, so this will not be a straight line. Here's the GlowScript graph, where drag was negligible. If you look at the velocity time graph, we can tell that the gradient was constant, meaning that the acceleration was constant, and that makes sense, then the gravitational force was the only force acting on our scrunched up paper. Here is the GlowScript graph with drag considered. We can tell that the acceleration was not constant because the gradient of the velocity time graph was changing. In fact, the acceleration was decreasing, and we can see that by the flattening of the velocity time graph. Here are the experimental versus theoretical model. The blue represents the experimental, the orange represents the computational model, and the gray represents the computational model where drag was considered. We can instantly see that there's an error with our experiment because the blue line did not match with the gray line initially, but they did meet up in the end. We can also tell that the gradients are increasing, meaning that the velocity is increasing, which is correct. We know that there's an acceleration causing the velocity to increase. Now, if you look at the end of the graph, there's a difference in the distance moved, and that was expected because drag was acting on the scrunched up paper, causing the distance moved by the paper to be less. Now let's talk about the sources of error. What if drag had a bigger effect? It would mean that the terminal velocity would have reached faster. And what if there was human error? That means that the point mass was insufficiently tracked on Tracker. Personally, I tried to use the center of mass to track the paper, but there's a lot of potential for error. Now, what if there was a technological error and Tracker wasn't working? It would mean that the displacement of the paper at specific times were inaccurate. Now, for our discussion, imagine that the object was initially thrown downward, with the terminal velocity in this case being the same or different from the case where the same object was initially dropped from rest. Justify your answer by using the computational model to examine the object velocity as a function of time in the case where the object is thrown downward initially instead of dropped from rest. Well, we know that the terminal velocity will be larger, and that was because downwards force is larger, and therefore it will require longer time for the drag to be equal to the downwards force. If we look at our equation, a larger time would mean a larger final velocity. Now, what does it mean? Examine the velocity versus time predicted by your models with and without drag. Which model, if any, predict the terminal velocity? Well, we know that where drag is negligible, the terminal velocity will not be reached because there's no upwards force. But with the GlowScript graph with drag, the graph started to flatten at the end, but it still has not reached terminal velocity because the time was just too short. Terminal velocity happens when the force of drag pointing up has exactly balanced force the force of gravity pointing down. What does this mean for the net force? This means that the net force is zero, so the acceleration is zero because of Newton's second law, which means that the velocity is constant. Thank you for listening.